Okay, folks, let's pick up right where we left off on the Clapeyron equation. And we're going to use this now to specifically get an equation that's going to allow us to calculate different melting points for the solid liquid boundary. Okay, so let's navigate down there, and here we go. So typically the solid and liquid boundary has a very steep and positive slope. That's due to the following. So we remember that dP by dt describes a phase boundary, and the Clausius-Clapeyron equation the Clapeyron equation specifically for that is fusion. So that's delta H fusion over T fusion delta V fusion. And I'm just going to leave the T there to make it a little bit easier to write. Okay. So what we should note here is the delta H of fusion is a positive quantity, and typically for all materials except, you know what, delta V fusion is a positive quantity. So that means when both of these things are positive, that owes to a positive slope, which we can see right there. Okay, so that's a positive slope. So, and this delta V of fusion being greater than 0, right, if we suss that out a little bit, that would specifically be the molar volume of the liquid minus the molar volume of the solid. And again, most things, the volume of the liquid is larger than that of the solid. Okay, but remember, for H2O, delta V of, I can't write and talk at the same time, delta V of fusion for H2O is negative. So that means for water and only water, it will have a steep negative slope. And this value is very steep because typically the difference in the volume between the liquid and the solid is small. So delta V is a small quantity, whereas delta H is a large quantity. So a large quantity divided by a small quantity gives us a very steep slope. Okay. So now we're going to do our trick where we divide and conquer and attempt to get a more specific equation for this phase boundary. So I'm going to separate the dt and the dp in the following way. I'm going to say dp equals delta H fusion divided by delta V fusion and times dt. And we'll assume for now that delta H and delta V are independent of temperature, which is generally like a pretty reasonable assumption. So when we integrate this, right, we can keep those two things on the outside of the integrand, noting that they are a constant. Oops, and sorry, there was supposed to be a t in there as well, right, divided by t. Okay. So now the result of this integral, I'm going to write this as the following. I'm going to go here, let's be consistent. And instead of saying final and initial, I'm going to say 1 and 2. And we'll see why that is, hopefully, in a moment. So now that's going to become P2 minus P1. And then now all that equals delta H of fusion divided by delta V of fusion. And the integral of dt over t, evaluated from 1 to 2, is going to be natural log of T2 over T1. And I'm going to rewrite this just a little bit differently. I'm going to say P2 equals P1 plus delta H fusion divided by delta V fusion and natural log of T2 over T1. So now what do I want to note about this 1 and 2 and so on? What this is really getting at is if I look at some point right here, I could describe that data point as P1, T1. And some other data point up the line there I could describe as P2, T2. So when we look at these designations, right, P2 corresponds to T2 and P1 corresponds to T1. And so what that means is my P1 and T1 are really like a reference point. Okay, and what we typically use for the solid liquid boundary is the triple point for that reference point. So if P1 is PTRP, that stands for P triple point, then that means T1 also has to be TRP, T triple. And so then if we were thinking about this as a useful equation, right, I'm going to go ahead and box this off. Now what that means is P2 is our Y value and T2 is our X value. Thus, we could create a smooth line across a broad range of Y and X, or pressure and temperature values. Okay. So now thinking about the units here, if we recall, right, whatever we have in the natural log, those will cancel, so it doesn't matter so much, even though we know we have to use Kelvin. But now we have a choice of what pressure units to use depending on what we've done for delta H and delta V. Okay, so let's look at those units really quick. So if I look at delta H over delta V, that's going to be a joule per meter cubed. And if you recall, a joule per meter cubed is a Pascal. So if we've used our molar volumes in cubic meter per mole, and we've used our delta H in joules per mole, then write that per mole and per mole unit cancel, and thus my pressure will be in Pascal. Okay. So that's all that I'm going to say about this video, this quick one. We're going to do another quick one describing the liquid vapor boundary. I'll see you then.